Hello, everyone, and welcome to your next talk of the day. I hope that you're all having a great day 3 so far, and it is my pleasure to introduce our next speaker. Next up, we have V.S. Subrahmanian, and he is the Dartmouth College Distinguished Professor in Cybersecurity, Technology, and Society, and the Director at the Institute for Security, Technology, and Society at Dartmouth College. And his talk today is entitled, Securing Enterprises with AI, Two Applications. So please give a warm virtual welcome to VS. Okay, you can come on out and join us. Camera, hello.
Hi.
Okay, have a great talk.
All right. Thank you. Ladies and gentlemen, thank you for joining this session. I'm going to be talking about how AI can be used to better secure enterprises. But before I do that, let me start by saying that the term AI was invented at Dartmouth in 1956 when a very famous conference called the Dartmouth Summer Conference on Artificial Intelligence was held, and it involved some of the founders of the field, John McCarthy, Marvin Minsky, Claude Shannon, and others. So I thought I'd put a little plug in for that before moving on to some of the work that's been done since then. So clearly, more than 60 years have gone by since 1956, and during the last several years, a huge amount of work has gone into the use of AI in better securing organizations. I'm not going to talk about all of these things in today's talk, but I did want to give you a quick overview of some of the cool ways in which AI can help secure enterprises. So for example, think about malware. Today, detection of malware, malicious apps on your phones are almost all done through a huge use of classification and machine learning algorithms. For example, we've used machine learning algorithms and developed machine learning algorithms to detect banking trojans, spyware, routing malware, and more. We've come up with methods to predict the family to which a malware sample belongs. Likewise, think about phishing. Whenever an email comes in, you need to predict, is this email a phish or a real email? Of course, adversaries are changing their attack vectors all the time. So phishing attacks are now coming from many previously unknown vectors, such as Twitter. So can we look at how adversaries use Twitter to carry out phishing attacks? Can we come up with understanding of how adversaries will adapt to classification algorithms as their phishing attacks are discovered and how they'll change? Social media. What about bots? We're coming up against an election in a few weeks. We need to identify bots and sock puppet accounts, multiple accounts operated by the same person, bot accounts that spread fake news and rumors. Deception is used all the time by attackers, but the good guys can use deception as well. And we've been exploring a number of ways by which the good guys can use deception. So to give you an example, I will be talking in more detail today about using deception to deter theft of intellectual property by automatically generating lots and lots of fake versions of documents. There are other forms of deception we look at as well. Can we mislead attackers to follow the wrong path even after they've penetrated our network by generating fake results when they scan the network? Can we optimally place honeypots so that when they visit those honeypots, we realize that they're up to no good? Can we merge the placement of honeypots with other traditional security devices, such as firewalls, such as intrusion detection programs, so as to better flag attackers? And then finally, last but not least, cyber risk. Virtually every enterprise, every CISO, every CIO in the world today wants to understand the level of cyber risk that his organization faces. This is critical for numerous reasons. Budgets, of course, are one. Second, he needs to know what kinds of risks he's protecting against. So as you all know, cybersecurity involves vulnerabilities in code, in hardware, in processes that are exploited by malicious hackers. And these malicious hackers write malicious pieces of code, typically called exploits, that exploit these vulnerabilities. So given that we know certain vulnerabilities and we know about them, can we predict which of these vulnerabilities will be exploited, when they will be exploited, how severe they will be? Those are all things that a CISO is going to spend a lot of time worrying about. And of course, once you know these things, the CISO has also got to figure out, what should I patch? What should I patch today as opposed to next week? What software should I deactivate? These are all important decisions with profound security implications. So today, I won't talk about all of these pieces of work, but I'll talk about two of them with in some detail. First, I'm going to talk about predicting which vulnerabilities will be exploited, when they will be exploited, how severe those vulnerabilities might be. Let's think a little bit about, and more importantly, if you're the CISO of an organization, can you predict what kinds of cyber attacks might come at you down the pipe? You may not know the full details of these attacks, but you want to have some idea what might hit your network. Let's think about how the vulnerability ecosystem works today. Every vulnerability is assigned, every known vulnerability, I should say, is assigned a number called a CVE number, which stands for Common Vulnerability and Exposure Number. So it's basically an ID for a vulnerability. Today, most organizations patch vulnerability after several conditions are satisfied. I've listed two of them. One is, of course, that a patch should be available. But another is that NIST, the National Institute of Standards and Technology, which manages the vulnerability process in the US, assigns something called a CVSS score. This is a score from 1 to 10, and each vulnerability that NIST analyzes receives a score on 1 to 10 along with a report that they generate. So most organizations wait for this report to be released by NIST before even patching the vulnerability. But in general, there is a big gap between the time a vulnerability's existence is first publicly disclosed and the time NIST assigns the CVSS score. So that gap needs to be thought about. Because that's a period of time when there's some exposure to the vulnerability for virtually any organization. Second, not all vulnerabilities are used in exploits by hackers. So if we think of these things, we have this quad chart that you kind of see on the right here. The x-axis is the time to attack. The bottom left corner, think of that as today. The times to the right are days in the future. And the y-axis reflects the severity of the attack on a 1 to 10 point scale, which is the scale used by CVSS. So you can look at the top left. These are the attacks, the vulnerabilities, that are very severe and are predicted to be very severe and likely to happen very soon. Whereas these at the bottom right are ones that are predicted to be much less severe, but also less likely to occur anytime soon. So if you're the CISO of an organization, you look and say, vulnerabilities that fall in this quadrant at the top left need to be dealt with now. They cannot be postponed. These things in the bottom right, maybe I can, push them off to a later date. And then these two quadrants here at the bottom left and the top right are somewhere in the middle. On the top right, you have very severe vulnerabilities, but not likely to happen immediately. On the bottom left, you have less severe ones, but likely to happen soon. So if you're a CISO, you've got to think about these things, balance the resources you have to fix your network, fix your enterprise IT system, and figure out, what to patch, what not to patch. So I wanted to say that you should think about how long this gap is between the time a vulnerability is first publicly known and the time NIST assigns a CVSS score. And also, what is the probability, what percentage of vulnerabilities are actually used in malicious exploits? So let me start with this number here. This is probably the one piece of good news you will see in cybersecurity, which is that according to a 23-month study we did of vulnerabilities between 2017 and 2019, only about 10%, just under 10% of vulnerabilities are actually used in exploits. But that raises a question if you're a CISO. Which vulnerabilities should I patch? Can I predict which these 9.9% of vulnerabilities are that are going to be used in exploits? That's what I got to protect against. But another shocking number is that there's a almost 4.5-month gap between the time a CVE number is assigned and the existence of the vulnerability is publicly known, and the time when NIST releases its CVSS report, telling people how severe that vulnerability is. And to make matters even more dramatically shocking, about half the exploits based on these vulnerabilities, 49.46%, happened during this 132.7-day gap. What that suggests to us is that hackers don't even have to find their own vulnerabilities. They look and say, oh, a CVE number was assigned on such and such date, it probably is not going to be fixed by most enterprises right away. Moreover, CVSS scores are only going to be released on average about 4.5 months later. Of course, some are released much faster. So a malicious hacker can say, well, I'm going to use this time to carry out an attack. And perhaps that's why this 49.46% of exploits based on these vulnerabilities happened during this window of terrible exposure. Let's take a look at a very concrete example. There was a Microsoft Office memory corruption vulnerability that was reported at some point. We don't know when this was reported to Microsoft or MITRE or NIST. The organization, MITRE and NIST work together in organizing and managing the National Vulnerability Database maintained by NIST. What we do know is that on the 31st of July 2017, MITRE created a dictionary entry for this vulnerability and assigned it a number, CVE 2017-11882. On November 14th, they published it to their website, but please note that a couple of sentences about the vulnerability were already available on July 31st. So 3.5 months after the dictionary entry was created, MITRE published the CVE to their website, and NIST released the CVSS report on this vulnerability on December 5th, about 3 weeks after this date, and about 4+ months after this date. Guess what? 1 week after MITRE published the CVE on their website, an attack that leveraged this vulnerability was used by the Cobalt hacking group, which stole passwords in order to hit bank accounts. We looked at the problem of using AI techniques to predict when these attacks will happen and how severe they will be, and if this vulnerability will be exploited or not. I won't talk about the last one due to time constraints, but our prediction model leveraged data from CVEs from 2 years, Twitter data discussing the CVEs, data from Symantec, as well as data from a few other sources. And we built out a machine learning model which involved natural language processing to extract a basic set of Twitter features, predictors of how many tweets will discuss this vulnerability in the future, and then we proposed some novel techniques. We built something called a cat graph, and associated popularity scores with the nodes in these graphs. Let me show you an example. The cat graph is actually quite huge, consisting of millions of nodes and edges. This shows you the immediate neighborhood around this CVE on the left, and this picture on the right shows you the immediate neighborhood around another CVE on the right. If you look at the CVEs on the left, the authors are shown in blue, the tweets are shown in green, and the CVEs are shown in red. And the size of each of these nodes is a measure of the importance of that node, or what we call a popularity score. This popularity score of an author node is a proxy for the influence and knowledgeability of that author about CVEs in general. The popularity score of a tweet is a reflection of the level of engagement and popularity of that tweet in terms of the number of people who see it, who perhaps retweet it, who perhaps like it. And likewise, the popularity score of a CVE is a proxy for the amount of information available about the CVE. We feed these into a machine learning model, and our best algorithm is able to predict this with a predictive accuracy of just under 12 days. So that means that today, if we put out a forecast saying that this particular CVE is going to be exploited according to our model on November 15th, 2020, then it's probably going to be exploited sometime in November, because our error rate is about 11.9. We can also predict the overall CVSS score. Recall that the CVSS score ranges from 1 to 10. We develop methods that take the language of the tweets into account, take the kinds of factors I just mentioned for predicting when the vulnerability will be exploited, and we fed it into graph convolutional networks with attention embeddings, and we're able to predict the actual severity of this vulnerability, the CVSS score, within 3 days of the first mention of that CVE on Twitter. So we're able to get that to about an error of 1.25. So that means that on average, if our algorithm says that the CVSS score of this vulnerability will be 9, it suggests that it's going to be somewhere between 8 and 10, very severe. On the other hand, if it was to say 5, it would mean somewhere between 4 and 6, much less severe. We're also able to predict a number of other things, including more detailed CVSS scores that I won't go into. And I'm going to move from here to the second problem I'm going to talk about today, which is IP theft. Virtually every organization that generates intellectual property in the US has faced the problem of IP theft. And a prior study by Symantec suggested that there is a 312-day gap, almost a year, on average, between the time an enterprise is compromised by a zero-day attack and the time the attack is discovered. So this means that over this period of 1 year, the adversary has ample opportunity to steal intellectual property. So what can we do about an adversary who's compromised your network and is stealing intellectual property, even though you may not even know that your network has been compromised until much, much later? So our approach to this was one of deterrence. Can we make it much harder for the adversary to figure out what is real and what is fake? And we try to do this by automatically generating fake versions of technical documents. So if you work, for example, for a high-tech company in the US, say a Lockheed Martin, generating lots of intellectual property, when you generate a document, we want you to interact with a system, such as our Forge system that I'll talk about in a minute, that automatically may generate, say, 99 fake versions of your real document, so that when the adversary compromises your system and steals documents, he's got to figure out which of these 100 versions is correct. Only one of them is correct. If he guesses wrong, even if he guesses right, he's not going to be 100% certain. And it's certainly going to take him a lot longer. It's going to add time, cost, and frustration to him as he tries to separate real from fake. Before I go into looking at long technical documents, here's some work we did with friends at the University of Padova in Italy on generating short sentences. And I'll ask you to look at these sentences, some from restaurant reviews, some from movie reviews, some from scientific papers, and say, can you tell which of these is real, which is fake? Take a look for a moment. So if you go to the next slide, the lines shown in red are all fake, synthetically generated by algorithms that we've developed. Authentic tasting sauce, fresh crust, looks like it could be from a review about a pizzeria. Russell Crowe's direction is far too predictable. Sorry, I don't want to say anything negative about Russell Crowe, but this is just an example of a synthetically generated sentence, which looks pretty realistic. But can we do this at the level of a technical document, which is much longer, say a patent or a scientific paper? So to do this, we use a mix of natural language processing. We take an original document in some format, extract concepts, and merge some similar concepts together, discard useless concepts, and then we build out two networks. A network that links the concepts together at the semantic level, and a network that does so at a syntactic level. And then we extend classical centrality metrics to associate a centrality measure on this, what's called a two-layer graph. We then solve an optimization problem and use an ontology to identify concepts in the original document that should be replaced, find replacement concepts for them, and we try to do this in a manner such that the fakes are believable to the adversary, but not too close to the reality. Let's take an example of what I mean by that. Suppose D here in the center of this picture is the original document. I don't want the fake documents that I show that are arranged around D in the circle, D1, D2, etc. I don't want the fake documents to be too close to D, because if they're too close to D, they're likely to be correct. We want these documents to be technically wrong. So we want them to be outside this inner circle that you see here. At the same time, we don't want them to be too far away from D, because if they're too far away from D, they're not going to be believable. They're likely to introduce concepts that are so ludicrous that the adversary will quickly figure them out. So they've got to stay inside this outer circle that you see here. So we want D1, D2, the fakes, to be not too near, not too far from what's being generated. We've developed an algorithm to do this at scale and developed a system called Forge. And right now, our deception rate on long technical documents such as patents is over 90%. So that means that even people who work in the field, who are forced to look at these documents, often choose the wrong one. 9 out of 10 times they get it wrong. And that's kind of what we're looking for. Can we force the adversary to spend a lot of time looking at the documents and still get it wrong often enough so that he spends time, he spends money, his level of frustration increases, and even if he guesses the right solution, he's not sure. That's what we want to inject. So again, a recap, I've talked about predicting cyber attacks and features of cyber attacks before they occur within 3 days of any discussion on Twitter of those vulnerabilities. I've talked about imposing costs and delaying and frustrating the attacker in cases of IP theft. And I do want to emphasize that there are many, many other applications of AI in security, some of which are shown on this slide. Thank you very much. And again, I'll close with a reminder that, even though I was not around in 1956, AI was invented at Dartmouth the term AI was first invented at Dartmouth in 1956. Thank you so much.